How to use this software. The rocket calculator has an intuitive interface with detailed hints. Read them and you will understand a lot more. For example, let's choose Falcon 9 version 1.1. This example is good because this rocket is designed in accordance with classical principles. The main rocket factors are presented as a percentage of the stage or rocket mass. Only the rocket lift-off mass and payload are presented as absolute values in kilograms. This approach is used because it is the relative ratios that are used to calculate the rocket effectiveness. For example, the dry-to-wet mass ratio is used in the Tsiolkovsky equation to determine the resulting rocket velocity. And the thrust-to-weight ratio is used in the formula for estimating velocity-gravity losses. This approach also allows us to better understand the basic principles of rocket design. For example, the optimal mass ratio of the second and first stages with serial staging is usually proportional to 1:7 or about 14%. To simplify the analysis of the results, we will equate the current payload to the nominal one. Try increasing or decreasing this ratio and you will see that in both cases the payload decreases. With this calculator you can also evaluate an existing rocket, in this case most likely you know its absolute weights of stages, propellants, engine thrust, etc. Then these values can be entered in the Output section once the Advanced button is pressed. Afterwards these values will be converted into relative values automatically. This tool allows you to simulate either a serial or parallel aka tandem staging, using booster stage option. However, in the second case the calculation accuracy will be lower. You can change the launch location and target orbit for any rocket and see how it impacts the payload. You can also enable air launch plane on any rocket and see the payload impact or assess the impact of reusability. Let's explore air launch. Choose Virgin Orbit Launcher 1. If we try to launch this rocket from the launch pad, we will lose 47% of the payload. On the other hand, if you launch Falcon 9 from an air launch, the gain will be only 19%. Which is due to the fact that the calculator does not take into account the possibility of rebuilding the first stage engines for a high-altitude launch. By the way, in the case of Falcon, this is really impossible to do due to the dense arrangement of the engines. It is interesting to note that the greatest gain in payload is provided by the increasing of speed, not altitude. Launching even at 50 km altitude does not provide a significant increase in payload. Hence the inefficiency of such projects that provide a rocket launch from a high altitude but without additional speed, for example, stratolaunch or rotary rocket. This calculator provides two options: calculation based on existing launcher, which allows you to evaluate its level of performance, or the engine-based calculation. In this case you can evaluate the performance of a hypothetical space launcher that can be created by selecting a certain number of existing engines. For the second calculation option, select Custom Rocket in the Select Rocket menu. If you choose Merlin 1D engine, you will get a result that is almost the same as Falcon 9 version 1.1. As I already said, this rocket complies with the classical design principles the launcher calculator based. To compare the effectiveness of different propellants and engine cycles, you can use the Averaged Characteristics mode, Set Averages. Let's select this option for the Falcon 9 and you will see that the payload is slightly reduced, proving that the real rocket has above average performance. Now we can try using methane instead of kerosene and see that it provides a 15% increase in payload. However, using a staged combustion engine will give an even greater increase even when using kerosene. If set averages option is not used, changes in propellants and cycle will not result in changes in payload. This is because the rocket factors are specified as directive, and changing propellants, for example, does not affect the engine-specific impulse, however does have an effect on the assessment of the achievability of this result. If you try to switch the Falcon 9 to solid fuel, the aggressivity index will increase to 18.6, which is significantly more than 12, which is the maximum value for that index. Which suggests that it is virtually impossible to create a solid rocket with such parameters. You can also apply limit to reasonable, in which case the rocket factors will be limited to the maximum possible for this case and the payload will be significantly reduced. In addition, you can try to estimate the capabilities of the rocket with the maximum achievable factors or even the minimum for type of rocket chosen by you. When choosing fixed design item, the engine's thrust and, in general, stage's mass are considered unchangeable. It is good for payload calculation of the existing rocket or selecting the optimal thrust-to-weight ratio or weights ratio between the first and second stages, otherwise the relative factors, which is better for the new launcher's designing. Let's conduct another illustrative experiment. Increase the thrust-to-weight ratio for the Falcon 9. Since the fixed design item is selected, the thrust of the engines remains constant, but the mass of the tanks and propellants is reduced to provide a given thrust-to-weight ratio. It is clear that the ratio of the payload to the weight of the rocket has increased, which is due to a decrease in gravitational losses, but the absolute mass of the payload has decreased. However, given that the cost of tanks and propellants is lower than the cost of rocket engines, the thrust-to-weight ratio for rockets is usually about 1.2, which is not the best choice for payload to the weight ratio, but better from an economic standpoint. Why then does the Falcon 9 full thrust have a significantly higher thrust-to-weight ratio? It was no longer possible to just increase the size of the tanks. The rocket would not be transportable on highways. This illustrates another way of rocket design, where prior decisions that are difficult to change force one to deviate from classical principles. And as the conclusion, you have the ability to export data for a user-created rocket. Just click the Export tab, and the link with the current rocket data in a special format will be entered into the browser address bar. Then you can send the link to your friend. Don't forget to change the default name new_rocket to what you want.